Hello and welcome to DragonRuby's array tutorial. In this video, we'll discuss arrays and all the ways that they can be used, as well as explain how methods like map, each, find all, and reject work. We'll talk briefly about ranges, combining functions, and go through some examples and sample apps to solidify your understanding. Let's get started. Arrays are one of the most useful data structures in any programming language, including Ruby, and are able to hold collections of elements of the same type. They can be used to output things onto the screen, like labels, sprites, and solids, and they can also store data and be used to perform mathematical calculations. We have DragonRuby open on the left side of the screen and the main.rb file open on the right. This file can be found by going into My Game and opening the app folder. First, we'll cover how to output objects onto the screen using arrays. We're only doing a quick run-through in this video, but for a more in-depth look into outputting objects on the screen using arrays, you can go through the GTK Ruby Primer by going into the Samples folder and opening the Beginner Ruby Primer folder. If we're outputting a solid, the first two parameters of the array are the x and y positions of the solid that we're making. The third and fourth parameters are the width and height of our object. The last three are the red, green, and blue saturations, which set the color. These parameters can be any number between 0 and 255. The first line of code creates a red solid, the second one creates a blue solid, and the third line creates a green solid. With the lines we've run, we've output a green, red, and blue box on the screen. In order to output a label, the array we use will hold the following parameters: the x and y positions of the label, or where the label appears on the screen, the text of the label, and the red, green, and blue saturations. The text of our label is the tick count or passage of time, but it can hold any string of text as long as it is surrounded by double quotes. When we save the file, the label is shown on the screen. In order to output a sprite on the screen, the parameters of the array are the x and y positions, the width and height of the sprite, and where the sprite's image is found. We have performed calculations that allow us to iterate through the .png files in the sprites folder, which again are explained in more detail in the GTK Ruby Primer. When we set the sprite image's path to iterate through the sprite folder's images, we get a moving dragon on our screen. All of the objects on our screen have been output using arrays, and showing things on the screen is of course an incredibly significant part of game making. Next, we'll talk about some important methods that can be used to manipulate arrays, like find all, reject, each, and map. Arrays store data, and we can create arrays that are derived from previous arrays. First, we'll create an inclusive range that holds numbers 1 to 20. We're using two periods to include the last value of the range, which is 20. To learn more about exclusive and inclusive ranges, be sure to go through the Intermediate Ruby Primer, which can be found by going into the Samples folder and clicking the Intermediate Ruby Primer folder. Ranges are covered in the looping text file. Anyway, we have our range, and we'll use 2a to make it an array, which we'll store in the 1 to 20 variable. This is our original array. The find all keyword allows us to find all values from the original array that we're looking for, which we'll then store in a new array. In this case, we're looking for all numbers in our 1 to 20 array that are divisible by 5. We'll find all numbers that go into 5 with a remainder equal to 0 and store it in our new array. Let's talk about what this line of code does step by step. These are all of the elements of the array. We're going to take the first element of the array, which has a value of 1, and say 1 modulus 5. The remainder is 1, but is that equal to 0? No. So 1 is not a number that meets our requirements, and we move on to the next element of the array, which is 2. We check if 2 mod 5 has a remainder of 0, which it doesn't. 3 mod 5 has a remainder of 3. 4 mod 5 has a remainder of 4, both not equal to 0. We get to 5, and we see that 5 goes into 5 with 0 as a remainder. It meets our requirements, so the value of 5 will be included in our new array, div by 5. Just because we found a match doesn't mean we stop though. We move on to the next element, which has a value of 6. 6 mod 5 is 1, which is not equal to 0. 7 mod 5, 8 mod 5, and 9 mod 5 have remainders of 2, 3, and 4 respectively. 10 mod 5 has a remainder equal to 0, so it meets our requirements and is added to our new array. 11 mod 5, 12 mod 5, 13 mod 5, and 14 mod 5 have remainders of 1, 2, 3, and 4. 15 mod 5 has a remainder of 0 and is added to our div by 5 array. 16, 17, 18, and 19 mod 5 have remainders of 1, 2, 3, and 4, so they don't meet our requirements. 20, the last element of our array, mod 5, has a remainder of 0 and is added to our new array. It seems like a lot of work to go through every element of the array and do our assessment, right? It's doable with 20 elements, but imagine if we had 100, or 1,000, or more elements in our array. Thanks to find all, we don't have to worry about doing the evaluation ourselves. Instead, we let find all take care of it. All the values from our original array that were divisible by 5 have been added to our div by 5 array, which is printed to the screen. A side note, if you want to open the DragonRuby console, all you have to do is press the tick key on your keyboard, which is located directly above the tab key. Another way to create an array of the same numbers, or numbers between 1 and 20 that are divisible by 5, is to use the keyword reject. Reject is used to omit all values from the original array that meet our requirements. In this case, any number that goes into 5 and has a remainder not equal to 0 is omitted from our new array. Again, we start at the first element of the array, which has a value of 1. 1 mod 5 has a remainder that is not equal to 0, so it is rejected from our new array. 2 mod 5, 3 mod 5, and 4 mod 5 have remainders not equal to 0 and are also rejected. 5 mod 5 is 0 and is not rejected. Since it is not rejected, it will be included in our new array. Moving on, 6 mod 5, 7 mod 5, 8 mod 5, and 9 mod 5 have remainders of 1, 2, 3, and 4, all of which are not equal to 0. All of these numbers are rejected. 10 mod 5 is equal to 0, so 10 is not rejected. 11 mod 5, 12 mod 5, 13 mod 5, and 14 mod 5 all have remainders that are not equal to 0 and are rejected. 15 mod 5 is 0, so 15 is not rejected. 16, 17, 18, and 19 are all rejected because they meet our requirements. 20 mod 5 is 0, so 20 is not rejected and is included in our new array. Again, iterating through each element of the array and doing an evaluation is too time-consuming for us to do on our own. The reject keyword saves us the time and trouble by performing the calculations by itself, definitely a lot faster than we did. All numbers that were not rejected are stored in our new array, which is printed to the screen. The keywords map and each go hand in hand, and whether you use each or map depends on whether or not you're trying to change your array. Each will perform an action on each element of the array. A simple example of when to use the keyword each is when you want to print all the contents of the array to the screen. The word puts automatically puts a new line after each number, unlike the word print. It starts at the first element of the array and prints it to the screen. Then it moves to the next one, prints it, moves on, prints the next element, and so on, until it reaches the end of the array. Each saves us the effort of doing the same calculations or performing the same action on every single element one by one, since it does it itself. Map is used if you want to transform data, and is used on arrays, ranges, and hashes. If we have an array of words, we can use map to capitalize all of them. In our example, we're going to use map to double every number in our original array. We'll use map on our 1 to 20 variable and double every number in the array. We'll store the results in the doubled array, which is printed to the screen. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and on it goes. All the methods we just learned can be combined to perform even more difficult tasks. Our next example is looking to find all unique Pythagorean triples between 1 and 100, which are then sorted by the area of the triangle. It sounds complicated, doesn't it? But if we use the keywords we've covered in this video, including find all, map, and each, we'll be able to figure it out in no time. The code for this example can be found in the Powerful Arrays text file in the Intermediate Ruby Primer folder. We're also going to need to use the words sort and unique. If you haven't seen sort or unique before, they can be found in the same Powerful Arrays text file, but we'll discuss them briefly in this video too so you don't get lost. Here's a little geometry review. Pythagorean theorem states that every right triangle has side lengths that satisfy the formula a squared plus b squared equals c squared. A Pythagorean triple consists of 3 positive integers that satisfy the formula and create a right triangle. C is the hypotenuse or the longest side of the triangle, while A and B are the other 2 sides, or the width and height. We're looking for all triples between 1 and 100, so the first thing we'll do is create an array of numbers 1 to 100. The keyword product is used to return an array consisting of all combinations of elements from all arrays passed into it. 1 to 100 dot product with 1 to 100 inside of the parentheses will give us all combination pairs of 1 and 100. One number represents A, and the second represents B. On this new array, we're going to call map since we're looking to transform the data we have and find our corresponding C values. They're called Pythagorean triples after all. Since A squared plus B squared equals C squared, we can conclude that the value of C is equal to the square root of A squared plus B squared, or rather, the square root of the width squared plus the height squared. This line gives us all of the possible triples. Pythagorean triples must be 3 positive integers, which means no decimals are allowed. In our next line of code, we're using our keyword findAll to find all triples from our vast selection that have a hypotenuse or C value that is actually an integer. We'll check to see if the C value is equal to the C value as an integer. If it is, we'll keep the triple. If not, we won't use it. We'll call map again on our current array of triples, prepend the and sign to a symbol, creating a lambda function, and call toI. Unique is meant to get rid of redundancy and remove repeating combinations. For example, if we had a combination that appeared twice, unique would remove the second appearance of it so only the first one remained. Sort serves to compare elements' values. If we call sort, our triples will show the smallest side first for A, the larger would be B, and the largest side, C, would appear third. It won't change the order of the elements, but inside of each element, it will change the order of the 3 values held. At this point, our remaining triples are all sorted in ascending order, and only unique combinations are present. The second part of our requirements say that the triples should be sorted by area of the triangle. In order to sort them by area, we need to first determine the area of all of the triangles. We'll call map on our array, and in addition to our width, height, and hypotenuse, we'll now also store the values of each triangle's area. The area of a square is calculated by multiplying the width by the height. So to find the area of a right triangle, which is half a square, we'll do width times height divided by 2. We'll now sort our entire array using sort by, which will reorder the elements in ascending order based on the area value. Our triples are stored inside of the triples variable, and in order to print the contents on the screen, we'll use the keyword each and print the width, height, and hypotenuse of each right triangle. We use string interpolation to do this since every triangle has different values that need to be printed. Our next example will use arrays and our keywords product, reject, findAll, and map in order to show colliding objects at different opacities. Each printed object that is not touching another object is given a full opacity, or is not transparent at all, while any object that is touching or intersecting with another object is shown to be more transparent or have a decreased level of opacity. Inside of DragonRuby's tick method, the first thing we're going to do is set grid, game, and outputs equal to args.grid, args.game, and args.outputs. We do this because outputs are a kind of argument, and so are grid and game. Typing args before each of these is redundant, so this line will save us a lot of typing later on. We're creating an object, ninjas, which goes into game. The pipes and equal sign mean that we'll set the value of ninjas to whatever follows the equal sign if the value hasn't already been set, like if it's nil or empty. Since DragonRuby's tick method runs at 60 frames in a single second, using the pipes and equal sign allows us to avoid resetting our values every single time the tick method is run. The ninjas variable will be set using the pipes and equal sign the first time the tick method runs, or if we use $dragon.reset to reset our game, but that's it. We're using 500 in our example, but we could very easily change that number so only 50 sprites are printed on our screen. Or any number really, as long as we use $dragon.reset inside the console to reset our game each time we change the number. We'll keep it at 500 and call map so we can perform an action on every element of the collection. The action we're performing in this case is declaring each of the 500 ninjas as new entities and setting their values. Using an array which is stored in rect, each ninja is first assigned a random location on the screen. The first 2 parameters of the array that is held in rect are the x and y positions based on the grid's width and height. Rand is what allows the positions of our objects to be randomized on the screen. The third and fourth parameters are the width and height of our ninjas, which we're setting to 50 and 50. You see how we said grid.w minus 50 and grid.h minus 50? That's because of the values of our third and fourth parameters. If we didn't subtract each ninja's width from the grid's overall width, the position of the ninja on the screen would exceed the screen's dimensions, and we wouldn't be able to see it. Same applies for the height. Anyway, we used map and set the size and location of each ninja, which are stored in rect. Considering how we have 500 ninjas, it's extremely convenient that we have map to use to do all the hard work for us. We were able to set values for hundreds of objects using only a few lines of code. Next, we're creating another object called collisions, which is stored in-game. We're using pipes and the equal sign to say, set the value of collisions to what is following the equal sign if the value has not already been set. First, we're calling product on our ninjas. So the ninja, its location and size, and other information is together as one single element. Next, we'll use reject to reject or omit any ninja that is equal to another ninja. We don't want repeats. After that, we'll find all the ninjas that intersect with another ninja. We'll see if the rect, which has the location of the ninja, intersects with the rect of another ninja. If they do intersect, they'll be included in our new collection, and we'll call map on it. All ninjas that intersect with another ninja will have their opacity set to a value of 128. 0 is completely transparent, and 255 is completely opaque, so the intersecting ninjas will be slightly transparent. We then call pairs to hash on our intersecting ninjas to create a hash with the ninja's entity ID as the key and the opacity of 128 as the value. This will come in handy later when we output our ninjas on the screen. We'll output our ninjas onto the screen by saying outputs.sprites and using the concatenation symbol. We'll call map on our ninjas and set some more values for each ninja. Inside the array, we have n.rect, which contains each ninja's x and y position and width and height, and then the .png file that has the image we're using to represent our ninja. We're using DragonRuby.png, so we'll see the DragonRuby logo as our ninjas. The third parameter, 0, is the rotation. 90 would rotate our ninjas 90 degrees. 180 would make them upside down, etc. The last parameter sets the opacity of the ninjas using the OR symbol. Either they're ninjas that intersect, which are in the hash we created before with the entity ID as the key, and have an opacity of 128, or they don't intersect with any other ninjas and have an opacity of 255, so they're completely opaque. We now have 500 ninjas on our screen, each showing the DragonRuby logo. As you can see, all intersecting ninjas are slightly transparent, and any that don't intersect are completely opaque. All the keywords we learned helped us to make this possible. We'll show the same code with 50 ninjas just to make the difference in opacity a little more noticeable. Now that we've gone through some examples that show just how useful map, reject, find all, each, and the other methods that we've covered are, we can go through some sample apps to show the different ways that arrays can be used when creating a game. First, we'll look at our sample solar system. Go to the Samples folder and click the Sample Workshop folder. The main.rb file is in the app folder, and you can see the solar system by running DragonRuby. The app shows the solar system. The sun is in the middle, and all of the planets are revolving around it in accordance to the real solar system model, like the distance of the planets from the sun and how fast their orbit is. We've got a little spaceship too that we can fly around in space using the arrow keys on our keyboard. This could not have been created without the use of arrays. The arrays in this example store information, output objects onto the screen, and can be found in many different places in the code. We won't get into the code for this app since we're focusing on the use of arrays, but for a more in-depth explanation on the code for this sample app and what each part of the code accomplishes, be sure to watch the tutorial video and presentation that are mentioned at the top of the main.rb file. So let's talk about all of the arrays that are used in this code. The first array is found in the defaults method, and this array is used to set the values associated with the stars of the solar system. We create 100 stars and call map on the collection, so we can collectively set values for all of the stars with minimal effort. We're using the first two parameters of the array to set the x and y positions of the stars, which are randomized. Rand places the stars in a random position within our screen dimensions of 1280 across and 720 up and down. The third parameter sets a random speed for the stars, since they're shown to be moving across the screen. The last three parameters set the red, green, and blue saturations and use rand to make the stars random colors. This one use of the word map and this one single array allow us to set the values of 100 stars to different values. Another array in this code serves to store information about all of the planets in the solar system. Each element of the array stores the name of the planet, which is a symbol, the distance of that planet from the sun, the size of the planet, and the number of days that make up 1 year, or revolution around the sun. We can call map on the array so that we can perform an action on every element of the collection, instead of performing that action one by one for each planet. Using map, we're making each planet a new entity and setting its distance, size, and year in days based on the values stored in the array, and we're also setting the path for each planet to an image found in the sprites folder, based on the planet's name. String interpolation comes in handy when the path name differs for each planet. Earth's path, for example, would be earth.png in the sprites folder. Another array in the code, found in the toSprite method, sets the values for the sprites we need to output on the screen, like the sun and the planets. The array specifically sets the x and y positions on the screen, the width and height of each entity, and the image path, or where the .png file for each entity is found. The toSprite function is called later on to position the sun on the screen as well as the planets. Map is called on the collection of planets, and toSprite performs calculations and uses the array values to output each planet on the screen. This single array is responsible for giving each of the sprites a special location on the screen, size, and image or appearance. We talked about how arrays are used to output objects like solids and sprites, and we see another example when we try to output our spaceship. The array contains the x and y positions of the ship, the width and height of the ship, 20 and 20, the ship's image path, which is the ship.png file found in the sprites folder, and the angle that allows the ship to move on the screen. That value is set when we declare the ship as a new entity. The calc method is where we call map on our stars collection and do the calculations necessary to allow the stars to loop back around on the screen each time their position exceeds the screen's dimensions. If we hadn't used arrays in this app, we would have had to set the values of each of the 100 stars one by one, which would have been exhausting. We wouldn't have been able to store information about the planets in a single location, and we wouldn't have been able to output them on the screen either. The arrays we used are fundamental to the functionality of this code, and that is why it is so important to understand how they work and how they can be used. Another sample app that uses arrays extensively is our game of Pong. You can find the main.rb file for this app by going into the Samples folder, clicking the Sample Game Pong folder, and opening the App folder. You can open the game by running DragonRuby. This game is a classic game of Pong, made for 2 players. There's a countdown in the middle of the screen, and the scores of the players are also output on the screen on their respective sides. There's a ball that moves across the screen, and each player has a paddle they use to hit the ball. These are the main parts of the game, and all of them are created using arrays. We won't go into too much detail about the code, but let's look at it and find all of the uses of arrays. We have a defaults method where all of the default values for the game are set, and then we have methods that set the values for both of the user's paddles and the ball using arrays. The first 2 parameters set the x and y positions or location of the paddles on the screen, and the third and fourth parameters set the width and height of the paddles for both players. It is the arrays that hold these values that give us the ability to define our objects and their characteristics in a way that is easy to understand, and also allow us to print our objects onto the screen later on. In the ball sprite method, the first 2 parameters set the x and y positions, and the third and fourth parameters set the width and height, or the size of our ball. In the render method, we're outputting many different kinds of objects on the screen, but no matter what kind of objects they are, they're all being output using arrays. We have a line running through the middle of the screen to separate the sides of the players, which we're outputting by saying outputs.lines with the concatenation symbol and setting the values for the line inside of the array. We're also outputting the scores of player 1 and also for player 2 by using labels. We're positioning the labels on the screen, setting the text, as well as some other values all inside of the array. We also do the same to print the countdown on the screen too. We're even outputting solids, specifically the ball, player 1's paddle, and player 2's paddle, by using the arrays we created in the ball sprite, player 1 paddle sprite, and player 2 paddle sprite methods. We've used arrays to output lines, labels, solids, all of which are vital to the functionality of the game. All of the sample apps that are available through DragonRuby use arrays to store important information, print or output different kinds of objects onto the screen, and perform calculations, generally in one single command using the keywords we've learned about in this video. Map, each, find all, reject, sort, and other keywords can save you a ton of time and effort when coding your games, so be sure to incorporate them in your code. Good luck and keep coding.